All right, so when we also talk about solutions, there's another technique, there's another concept that is often used in conjunction with solutions, and that is a technique called dilution or dilution, however you want to pronounce it. And dilution is a process where we make a less concentrated or a more dilute solution from one that is a more concentrated one. All right. So if you think about, when you dilute something, you're adding more solvent to that original solution. Okay. And in most cases, that solvent is water. So usually H2 for aqueous solutions. So if you add more solvent, what happens to the volume? Well, the volume obviously has to increase. And if the volume goes up, what happens as a result is that the concentration has to go down. So the concentration decreases. And overall, the reason why that happens is because the number of moles, we don't change the number of moles of the solute, that stays constant. So moles of solute is constant. Okay, so these are the main things that happen when you dilute something. If you can imagine, if you have an orange juice concentrate that you buy from the supermarket, well, how do you make it into a form that you can drink? Well, you take a can of it and you dilute it with water, and you make it more dilute or less concentrated to a form that you can drink. You don't change the amount of the original orange juice concentrate, right? That's the solute, that stays the same. What you do is you change the volume by adding more solvent, and as a result, the concentration decreases. That's the same thing that we're going to see when we dilute solutions in the laboratory, for example. And when it comes to dilution, there's one very important equation that we need to know. That's the dilution equation. And the dilution equation relates initial conditions, which we'll call the concentrated conditions, to the final conditions, what we end up with. We'll call those final conditions the diluted conditions. So concentrated, what we start with, and then we have our dilute. So the concentrated solution that we start with is often referred to, is often called a stock solution. Okay, and this is really how solutions are made in the laboratory, for example. We make a stock solution that is very concentrated, and then we can dilute that however we want to make solutions of different lower concentrations, depending on what it's needed. So this dilution equation relates initial conditions to final conditions, and we can apply this to any concentration unit. It doesn't have to be just molarity. So the equation goes like this. It goes C1 times V1 is equal to C2 times V2. And the ones here that we see as the subscripts, these are our initial conditions. So those are the concentrated solutions that we're starting with. The C here represents concentration. The V here represents volume. So if we multiply initial concentration by initial volume, I shall end up with the product of the final conditions. Again, the final concentration times the final volume. And if you actually substitute those units in here, you'll actually see why the number of moles don't change, right? So if I have my initial concentration, right, let's say moles over liters. If I times that by my initial volume in liters, so liters cancel out, I have moles on this side. So let's say moles initially, and then if I times now my final concentration, so moles over liters, times the final volume in liters. Okay, liters go away. I end up now with the moles at the end, right? The number of moles don't change when you dilute something. It's the same number. What changes is the volume, which makes the concentrations decrease. All right, so let's take a look at a couple examples. So it says in an experiment, the student needs 1 liter of a 0.4 molar KMnO4 potassium permanganate solution. A stock solution of 1 molar is available. How much of the stock solution is needed, right? So the terminology here is important. We're starting off with a stock solution, okay, which is going to be our concentrated solution, right? That's what we're starting with. That's my initial. So this here will be my initial concentration, 1.00 molar. And then what we're ending up with over here, this is my final concentration, C2.400 molar. Then I have my final volume that I want to get. That's my V2. That's 1.00 liters. So in questions like these, right, that's the first stumbling block or the first hurdle that you need to get over, which is to identify what are the different things that you're provided with. You're not told this is V1 or V2 or whatever. You have to figure that out from the problem, and then you can stick it into your dilution equation. Again, the dilution equation that I just wrote down may look slightly different, but it means the same thing. So the one that you'll see in your textbook, for example, says molarity of the C. This is the concentrated solution times the liters of the concentrated solution. This is the same as C1 V1 is equal to C2 V2. Okay, they're just using molarity and liters instead of concentration and volume respectively, but it's the same idea. So what we need here, we need the volume of that stock solution. Our initial, our V1 is what we need, or our L subscript C is our unknown. So we can take our C1 V1 equation, our dilution equation, and we can solve it for V1, right? So if I rearrange, V1 is equal to C2 V2 over C1, I just then need to plug in my values. My C2, my final concentration is 0.400 molar. Final volume is 1.00 liters. Keep track of your units because this will confirm that you've done the algebra correctly. Divide that by 1.00 molar. Molarity cancels. Okay, I end up with liters as the only unit. Makes sense. I'm trying to find a volume. And that would be 0.400 liters as my final volume of that. I'm sorry, as my volume that I need of that stock solution. All right, so we'll measure that out. And then to make it to the final volume of 1 liter, we'll just add the remaining volume to get up from the 0.4 liters all the way up to the 1.0 liter and the whatever container or measuring device we're using. It doesn't matter what unit of concentration or what unit of volume that you use, just as long as they're the same, so they can cancel out along the way. So you can have units of mils as long as there are mils on both sides. You can have units of molarity, which is what we're using, as long as molarities on both sides, but it can be other units as well. Another sort of technique, sort of similar to regular dilution, is called serial dilution. Okay, and in a serial dilution, what this means is that we're going to start off with a stock solution. And what we're going to do with that stock solution is we're going to dilute it. We're going to end up now with a new solution. And then we're going to take that solution, we're going to dilute that again to end up with our second new solution. And then we're going to continue doing that, dilute the previous solution to end up with our new solutions after each turn. Because we're doing it in series, we're doing it one after the other. This is called serial dilution. And it's a very important technique that's used to make or to make, yes, I'm sorry, to make solutions of really, really small concentrations if we need them. Okay, so serial dilution, we take our stock solution, dilute it once, we take that new solution, we dilute it a second time, then dilute that third solution to a fourth solution, we take that, and if we needed to, we can keep going over and over and over again and keep diluting it in series. We can repeat that as many times as needed. Okay, so let's take a look at one example involving serial dilution. So it says starting with a 2.0 molar stock solution of HCl, hydrochloric acid, right? So this is our stock. What is this, 2.0 M HCl. 4 standard solutions are to be prepared by sequentially diluting 10 mils of each solution to 250 mils. Determine the concentration of all 4 solutions and the number of moles of HCl in each. All right, so we're going to take this, and what we're doing, this is our stock. We're going to take 10 milliliters out. Okay, and we're going to dilute this to, what does it say, 250 mils. And then we're going to take 10 mils out of that, dilute that to another 250 mils. Then we're going to take 10 mils out of this and dilute that to 250 mils, etc. Okay, so again, we're taking our stock solution, we're diluting it by taking 10 mils each time from the new diluted solution to make the next one in the series. So we'll take a look at the first couple here, and then the technique is going to be the same for all of them. So it says determine the concentration of also all 4 standard solutions and the number of moles in each. Let's take a look at the first dilution, this first one here. So in this, going from the stock to the first dilution, our initial concentration, C1, is 2.0 molar. Our initial volume that we're taking there is 10 mils. Okay. Our final volume that we're diluting it to is 250 mils. And I'm not paying attention to sig figs right now. That's not the point of this, but you wanted to pay attention to that. We need to calculate what the final concentration is, right? So if I need to use my C1 V1 equals C2 V2, I need to solve for V2. I'm sorry, I need to solve for C2 in this. So my C2 there would be equal to C1 V1, right, over V2. I substitute these values in, I end up with my C1, which is 2.0 molar times my V1, which is 10 milliliters, divided by my V2, which is 250 mils. Okay, milliliters go away. I evaluate that. I end up with my concentration of this solution here being equal to 0.08 molar. Okay, and this is important now. When we get an answer, you want to think about, does it make sense? Well, what happens when you dilute a solution? What happens to the concentration? Well, the concentration should decrease after each of these steps, right? And it does. It went from 2 to 0.08. All right, and then, so that's at the end of the first step. Once we know how much of the concentration, this is my C2, right? The other thing I need to do is to figure out the number of moles of HCl in that solution. Well, I have 0.08 molar, that means moles of HCl for every liter of solution. Do I have a liter of solution? No, I have 250 mils. So if I take that concentration and multiply it by the volume now, which has to be in liters because it needs to cancel out, liters go away, that will give me my number of moles in that solution there, which would be, let's see, 2.08 times 0.25, that'll give me 0.02 moles. Okay, so that's going to be for the first step. Now for the second dilution, so going from here now to this one, now I'm relating these two. Right there, we'll try to keep this color-coded. My initial concentration there, okay, with my C1 would be the C2 from the previous step, so that's 0.08. My V1 that I'm using there is 10 mils again. My V2 I want to end up with is 250 mils, and then my C2 is what I need to find. Okay, that's my unknown. Again, I do the similar rearranging, so my C2 would be equal to C1 V1 over V2. I substitute those values in. So my C1 there is 0.08 molar. My V1 is 10 milliliters. And my V2 there is 250 mils. Let's go away. So my C2 then, which is actually my third, this one down here, this concentration that I calculate there would be 0.0032 molar. And if I want to find the number of moles in that now, I would take my concentration and I would times it by the volume. So 0.0032 moles of HCl for every liter times the volume that I have, which is 250 mils, which is 0.250 liters. That goes away, and that'll give me 0.0008 moles. Okay, and we keep doing that for the remaining ones. We relate this one here to that one, right? So if I substitute that in, this one here would be my C1 and V1. Well, the V1 there would be 10 mils, and then my C2 and V2 would be in the last one in the series. So the calculations are the same in each step. The numbers are what are going to change, and specifically the initial concentrations are what change from one step to the next. Okay, the next thing we'll take a look at here is how, in addition to looking at the concentrations of the entire solution, we can also calculate. So we can also determine the concentrations of individual ions in solution. Okay, and here what we're going to do is take advantage of, we're going to use our chemical formulas. And specifically the subscripts ratios to help us figure this out. All right, so it says, using square brackets notation, express the concentration of the chloride ion in a solution that is 1.02 molar in AlCl3. So let's take a look at that one specifically. So we're given here the concentration of AlCl3 is 1.02 molar. Okay, what this means, again, in a way that makes sense to us, is that the concentration is 1.02 moles of the solute, aluminum chloride, AlCl3, for every liter of the solution that we have. All right, the question is not asking us for the aluminum chloride. It's asking us to determine the concentration of just the chloride ion, right? The chloride ion is the Cl minus. Well, what is it about the AlCl3, right, that is going to tell us the relationship between the chloride and this thing? Well, if we look at the chemical formula for aluminum chloride, right, if I just look at the subscripts, if I have 1 mole of AlCl3, this means that it contains 3 moles of the chloride ion, right? And that has to be the case because 1 mole of AlCl3 also has 1 mole of the aluminum ion, right? Which is the Al3 plus. So we need the 3 moles of the Cl minus to cancel out that 3 plus from the aluminum, the charge on the aluminum, right? So this is important because now what we want to do, 1 mole, let's write that out completely. We want to relate the aluminum chloride to the thing that we want, which is the moles of the chloride. So we can get that from the chemical formula, which is this one here. So we can say 1 mole of aluminum chloride, AlCl3, rewrite that. 1 mole of aluminum chloride contains 3 moles of the chloride. I can write that as a conversion factor. So 3 moles of Cl minus, and I can do with that what I do to all conversion factors. I can flip it and put the 3 moles of the chloride on top for every 1 mole of the AlCl3 on the bottom. So now I get this information here just from the concentration that's given. Okay, so I really don't need to do a whole lot with that except to use it. So I have 1.02 moles of the AlCl3 for every liter of the solution. Now I can take this relationship that relates the aluminum chloride to the chloride. So I have 3 moles of Cl minus for every 1 mole of the aluminum chloride. And guess what? Moles of aluminum chloride cancel out. So now the units that I end up with would be moles of Cl minus for every liter of the solution. So this then would be molar of chloride, which is what we're trying to find, right? 1.02 times 3, that would be what? 3.06 molar chloride. And that makes sense, right? Because there's a 3-to-1 ratio. So multiplying that initial concentration by 3 is what we would get. So we want to think about, right, the ions that are present. And again, we can figure that out just based on the chemical formula, right? We can figure out the ions that are present. For example, in aluminum chloride, right, that's made up of the aluminum ion, and we have to have 3 of the chlorides. So there's a 1-to-3 mole ratio between the thing that we're given, which is the aluminum chloride, and the thing that we want, which is just a chloride ion. So we can calculate concentrations of specific species, in this case, ions, in that solution.